Well, here's the day. Today we prove the Pythagorean theorem. And since it is a theorem and they all have conditional form, we could, of course, consider its converse as well. And this is one of those geometrical theorems that has a true converse. So we will prove both the Pythagorean theorem and the converse of the Pythagorean theorem. And, excuse me. So here we are back to where I wanted to be. So the Pythagorean theorem itself, what does it say? If a triangle is right, then the sum of the squares of its legs equals the square of its hypotenuse, which of course you knew. So here's a nice little picture for us. We have a right triangle ABC, right angle at C, with side lengths little a, little b, little c, as we always do. The little a is opposite the uppercase A and so on for B and C. And then we have that a squared plus b squared is equal to c squared. So let us discuss how this will be proven true. Well, here's the outline of the proof, the basic procedure. We'll drop in the altitude to the hypotenuse. So that's the sort of situation that we had in section 8.1. And then we'll make use of a theorem that we proved in section 8.1 about geometric means. And then we'll just do a little bit of algebra. And at the end, the Pythagorean theorem will pop out. So here we go. What is that 8.1 theorem that we will need? Well, it's the one that says that the leg of that original right triangle, or each leg of that original right triangle ABC, is the geometric mean of the whole of the hypotenuse and the piece adjacent to that leg. So for instance, I don't know, just consider one of these. So we'll take the leg AC, so there it is. It's the geometric mean of the whole of the hypotenuse, which is that AB, and then the AM is the piece of the hypotenuse which is adjacent to that leg of AC, and the other one says basically the same. All right, so simplify just a little bit. We've added some labels to sides, and then what we need to do now is we need to prove our theorem. So here we go. So by a result, proven in 8.1. So here's what we'll have. We'll have a pair of proportions. So each leg is the geometric mean of the whole of the hypotenuse and the piece adjacent. So we'll do A first. A is a leg, so it's the geometric mean of the whole of the hypotenuse, which we will call just C, and then the piece of the hypotenuse which is adjacent to that A, which is the Y. And then we can do the same with the B as well. So that leg B is the geometric mean, so there it is in the position of the geometric mean, of the whole of the hypotenuse and the piece adjacent to the B, which is the X. So now let us cross multiply. And I think that you will be astounded by how remarkably simple that is. So we'll cross multiply each. So for the first, we get a squared is equal to cy. And for the second, we get that b squared is equal to cx. And then simply add. That is, add the left sides, add the right sides, and this, of course, is just the postulate that equals added to equals or equals. So we get that a squared plus b squared, which is remarkably suspicious, right? Because that's what we're supposed to get. And then when we add the right sides, we get cx plus cy. But note this, cx plus cy is equal to, and let us factor the c out of that, there's a common factor of c, is c times the quantity x plus y, which is equal to, and then pause there for a moment and think about this, x plus y is simply the two pieces of the hypotenuse, so x plus y is equal to c. So this is c times c, of course, which we would write as c squared. So then, and it's really just as simple as that. So then a squared plus b squared, which was equal to cx plus cy, is equal to c squared. And with that, we are done. And, this is one of those examples of how it is that once all that prior machinery is in place, this new result is really quite easy to use, to prove. And it might be worth our while to stop and think about what that prior machinery is. Well, we use that result from 8.1 about geometric means. And how did that get proven? Ultimately by angle-angle similarity. And then, well, that's it. As for really what is the machine that drives this, it's angle-angle similarity. We have similar triangles when we drop the altitude to the hypotenuse, um, proven by angle-angle similarity, which allows us to write proportions and then just a bit of algebra. So a good way to sum up what we've done here is that the Pythagorean theorem is a relatively quick, relatively easy consequence of angle-angle similarity together after one's made that construction of altitude to hypotenuse. All right, so now for the Pythagorean converse. Okay, so the Pythagorean theorem itself says that if a triangle is right, the sum of the squares of the legs equals the square of the hypotenuse. The converse of this would say if the sum of the squares of two sides of a triangle equals the square of the third, then that triangle is right. Now you might notice something about how I said this. I didn't say that if the sum of the squares of the legs equals the square of the hypotenuse, then the triangle is right, because that's not really the right way to put it. Because if I say if the sum of the squares of the legs, I just assume that it is a right triangle because only right triangles have legs. So instead, we ought to be non-committal about this triangle and instead just talk about sides. Okay, of course, we will conclude that ultimately it's a right triangle. But the point is that we wish to conclude that we should not assume that we have a right triangle when we set this up. Okay, so what this gives us, or what it will give us once we prove it, is really a right triangle test. Okay, so it says that if the sides of a triangle satisfy the equation a squared plus b squared equals c squared, then that triangle has to be right. And of course, the assumption here is that c is at least as great as a or b. So if you order the sides from least to greatest, and the sum of the squares of the first two is equal to the square of the third, it's a right triangle. And of course, if that's not true, it's not a right triangle, because by the Pythagorean theorem, if it were a right triangle, that equation would be true. So here's the official setup for the proof of the Pythagorean converse. So we have a triangle ABC with C at least as great as A or B, that is A less than or equal to C and B less than or equal to C. And we're also given that a squared plus b squared equals c squared. We are, in this case, able to prove that the triangle ABC is right. Now, the proof that we will give is essentially Euclid's proof. And Euclid's brilliant first step is to begin with a construction. So we construct a right triangle RST with its right angle at T so that its legs are equal to A and B respectively. And it might be worth our while to pause, and here's a picture of that. It might be worth our while to pause and to convince ourselves that this is an allowed construction. Okay, so first of all, we did make a right angle. Okay, so that's right angle RST, and then on one side we marked out a length equal to A, that's the R, and then on the second side of that right angle we marked out a length equal to B, and that is our S. So the construction rules that we used here, and I won't take the time to write this out, but the construction rules that we used were, first of all, construct an angle of a given measure, and that's the right angle. And then the second part of the construction was to mark out pieces of the two sides of that angle equal to given lengths. And these are both certainly allowed constructions. We can construct angles of whatever measure we choose, and then from array we can pick out a piece of whatever length we choose. Okay, so this is certainly an allowed construction. And then on the worksheet, I will let you work this out. Okay, you will find that it's not a particularly difficult proof to do, and I would like you to be able to discover it yourself. I give you a little bit of help with that. And then just finally, to show you how we now do have a test for right triangularity, consider a triangle of side lengths 5 and 12 and 14. And we should note that such a triangle does exist because the sum of any two sides is greater than the third side. We call this the triangle inequality in our chapter on inequalities. So such a triangle as this does exist. And then we wish to know whether it is a right triangle. Okay, so the question you have to ask is this. Is 5 squared plus 12 squared equal to 14 squared? And then, of course, one can, oops, let me make that a bit neater. One could easily answer that question. Calculator, perhaps. So is it the case that 5 squared plus 12 squared is equal to 14 squared? If that is true, then it is a right triangle. And that's the converse of the Pythagorean theorem. And if it isn't true, then it's not a right triangle, because by the Pythagorean theorem, if it were a right triangle, then 5 squared plus 12 squared would equal 14 squared.